Right now, somewhere beneath the surface of the Pacific Ocean, there's a mountain range longer than all of Earth's continents combined. It has never been fully explored. Most of it has never been seen. It is not in another galaxy, not on a distant moon, not somewhere that requires decades of space travel to reach. It is here, on this planet, in the ocean, that covers 70% of Earth's surface, and we know less about it than we know about the surface of Mars. This is not an exaggeration made for effect. It is a precise, measurable, scientifically documented fact. The ocean floor is the least known large-scale environment on Earth. Not the least known environment in the solar system, the least known environment on this planet. In the era of satellites, deep space telescopes, and rover missions to other worlds, the floor of our own ocean remains, in most of its vast extent, unmapped, unsampled, and unseen. What lies down there, what creatures live in it, what geological processes shape it, what chemical reactions sustain it is, in the most literal sense, unknown. If you enjoy drifting into the deep ocean and discovering what lies beneath, please consider liking and subscribing. It truly helps more than you know. Are you ready? Let's begin. In 1972, the Apollo 17 mission took a photograph of Earth from space. The image, known as the Blue Marble, became one of the most reproduced photographs in history. It showed a planet almost entirely covered in water, a blue sphere hanging in the black of space, its continents visible as irregular brown and green patches amid the overwhelming blue. The photograph made something viscerally apparent that maps and globes had always implied but never quite communicated. This is an ocean planet. The land is the exception. The water is the rule. And yet, in the decades since that photograph was taken, the scientific resources of humanity have been directed overwhelmingly toward the sky. Space agencies have been funded. Telescopes have been launched into orbit. Rovers have been sent to Mars. Probes have been dispatched to the outer solar system, to Jupiter and Saturn and beyond, traveling for years and decades to reach destinations billions of kilometers away. The justification for this investment has always been partly practical. Space holds resources, communications, satellites, navigation systems, and partly philosophical, the desire to understand where we came from, whether we are alone, what the universe is made of. These are legitimate questions. The investments have produced extraordinary science. But in the process, something has been systematically neglected. The ocean floor present, accessible, directly relevant to the functioning of the planet's climate and ecosystems, has received a fraction of the resources directed towards space. The result is an asymmetry in human knowledge that is, when you examine it carefully, almost absurd. We have mapped the surface of Venus, a planet shrouded in clouds so thick that its surface was entirely invisible until radar imaging was developed to a resolution of 100 meters. We have mapped the surface of Mars at resolutions of less than a meter in some areas. We have mapped the moon so thoroughly that individual craters a few meters across are cataloged. And we have mapped roughly 20 to 25% of Earth's ocean floor at meaningful resolution. The ocean floor is not far away. The average depth of the ocean is about 3.5 kilometers. The deepest point, the Challenger Deep in the Mariana Trench, is approximately 11 kilometers down. These are not astronomical distances. The distance to the moon is roughly 34,000 times the depth of the Challenger Deep. The distance to Mars, at its closest approach to Earth, is roughly 50 million times the depth of the deepest ocean trench. And yet, we have more detailed maps of both those worlds than we have of the floor of our own ocean. How did this happen? The answer involves a combination of technological difficulty, institutional priorities, and a particular cultural bias toward the visible and the distant that has shaped the history of exploration in ways that still influence how we allocate scientific resources today. Understanding how the ocean floor came to be less well mapped than Mars requires understanding something about the relationship between human curiosity and human attention, about what captures the imagination and what does not, and why the floor of our own ocean, enormous and present and profoundly important, has spent the last century in the shadow of the sky. The mapping of planetary surfaces from space became possible in the mid-20th century, when the development of radar and other remote sensing technologies allows scientists to map the topography of distant worlds without physically visiting them. A satellite orbiting Mars can send radar pulses toward the surface and measure the time they take to return, building up a detailed picture of the terrain below from tens of thousands of kilometers away. The technique is elegant and efficient. A single satellite in the right orbit with the right instruments can map an entire planetary surface over the course of months or years without any human presence on the ground. The ocean floor cannot be mapped this way. Radar does not penetrate seawater. The electromagnetic waves that work beautifully in the vacuum of space are absorbed by the ocean within meters of the surface, making it impossible to image the seafloor from above using the same techniques that have produced our detailed maps of other planets. The only way to map the ocean floor in detail is to get close to it to lower instruments through kilometers of water until they are near enough to the bottom to produce useful measurements. This is slow, expensive, and requires specialized ships and equipment that are far more logistically complex to deploy than an orbiting satellite. There are ways to get rough estimates of ocean floor topography from space. Satellite altimetry, the precise measurement of the height of the ocean surface, can detect subtle variations caused by the gravitational pull of underwater mountains and trenches. Where a large underwater mountain exists, its extra mass pulls water slightly toward it, creating a very slight elevation in the sea surface above it. Satellites can detect these variations and infer the presence of major topographic features below. This technique has been used to produce global maps of ocean floor topography at a resolution of roughly 1 to 2 kilometers, sufficient to identify large features like mid-ocean ridges and major trenches, but not sufficient to resolve the smaller scale features that dominate the ecological and geological character of the seafloor. 1 to 2 kilometers of resolution sounds useful until you consider what it means in practice. A resolution of 1 kilometer means that any feature smaller than 1 kilometer across is invisible in the map. The vast majority of the topographic features of the ocean floor, the hills, valleys, smaller seamounts, volcanic structures, and geological formations that constitute the actual texture of the seafloor are invisible at this resolution. The maps derived from satellite altimetry are, in the language of cartographers, small-scale maps. They show the large picture but obscure the details. The ocean floor, at the resolution we have mapped most of it, is like a photograph of a city taken from so far away that individual buildings are invisible. You can see that a city exists. You cannot navigate it. The comparison with Mars is instructive precisely because Mars presents a more extreme version of the same challenge, and we have solved it there. Mars has no global ocean. Its surface can be imaged directly from orbit. We have sent multiple orbiters to Mars over the past 5 decades, each with more capable imaging systems than the last, and the cumulative result is a detailed global map of Martian topography at resolutions that reveal features just a few meters across. We have sent rovers to the Martian surface that have driven dozens of kilometers, imaging their surroundings continuously, producing datasets that allow scientists to examine individual rocks. We have a detailed, high-resolution, globally comprehensive map of a planet approximately 150 million kilometers away. The ocean floor, 3.5 kilometers below the surface on average, awaits a comparable mapping effort that has not yet happened. The technology to do it autonomous underwater vehicles capable of sustained operation at depth, multi-beam sonar systems that can map the seafloor in swaths as vehicles move across it exists. What has not existed until recently is the combination of will, funding, and coordinated effort required to deploy that technology at global scale. The Seabed 2030 project, a collaboration between the Nippon Foundation and the General Bathymetric Chart of the Oceans. It was launched in 2017 with the goal of producing a complete high-resolution map of the ocean floor by 2030. As of the mid-2020s, the project has made substantial progress. The mapped fraction of the ocean floor has increased significantly since the project began. But the task remains enormous. The ocean floor covers more than 360 million square kilometers. Mapping it at the resolution required to see the features that matter takes time, money, and ships. The disparity in our knowledge of the ocean floor compared to other planetary surfaces is not, therefore, a mystery without explanation. It has a clear cause: the combination of technological difficulty, institutional neglect, and the cultural gravitational pull of space exploration that has, for decades, directed the best instruments and the largest budgets toward the sky. Understanding this cause does not make the disparity less significant. The ocean floor is here. It is close. It affects the planet in ways that the surface of Mars does not. And it is, in most of its extent, unknown. The mid-ocean ridge system is the most dramatic example of what this ignorance conceals. This is the longest mountain range on Earth, roughly 65,000 kilometers of underwater mountains, running through every ocean basin, circling the planet like the seam on a baseball. The ridge marks the boundaries between tectonic plates, the places where new ocean floor is continuously being created as plates pull apart and magma rises from below to fill the gap. It is the most geologically active terrain on the planet. It is the location of more volcanic activity than all of the world's surface volcanoes combined. And it has been directly observed in any detail over a tiny fraction of its total length. What lives on the mid-ocean ridge? What organisms inhabit the hydrothermal vent systems scattered along its length? What geological processes shape its terrain? What chemical exchanges occur between the hot rock and the overlying ocean is known in outline, but not in detail. The outlines were established by the expeditions of the past 50 years, the work of researchers who went to specific locations and looked carefully at what they found. The details, the variation from one location to another, the ecological diversity across thousands of kilometers of ridge terrain, the response of vent communities to changes in geological activity remain largely uncharacterized. The seamounts represent a second category of poorly known terrain. Seamounts are underwater mountains that rise from the ocean floor but do not reach the surface. There are estimated to be more than 100,000 seamounts in the world's oceans, defined as underwater mountains rising more than 1,000 meters from the surrounding seafloor. Fewer than a few hundred of these have been studied in any biological or geological detail. The rest are known. Primarily from bathymetric data, we know roughly where they are and how tall they are, but their ecological character is unknown. Seamounts are among the most productive and biodiverse habitats in the deep ocean. Their slopes concentrate nutrients and support communities of organisms that are often quite different from those on the surrounding abyssal plain. They are, in effect, biological islands, isolated habitats that support endemic species found nowhere else. How many species live on the world's seamounts that have never been described by science? The honest answer is that we do not know, and we cannot know until we go and look. Estimates, based on the rate of new species discovery in the small fraction of seamounts that have been sampled, suggest that the total number of undescribed seamount species could be in the tens of thousands. These are not microbes or microscopic organisms. They include fish, corals, sponges, crustaceans, echinoderms, and other large, complex animals that would be immediately recognizable as remarkable if anyone were to observe them. The abyssal plain, the flat, sediment-covered terrain that occupies the majority of the ocean floor, at depths between 3,000 and 6,000 meters, presents a different kind of unknown. It is not unknown for lack of exploration in the way that the seamounts are unknown. It has been sampled repeatedly in many locations, and the samples have revealed a community of organisms that is more diverse and more interesting than early researchers expected. What remains unknown about the abyssal plain is not its broad character. We know it is inhabited. We know it is ecologically functional. We know something about the organisms that live there, but its fine-scale variation. The abyssal plain is vast, and the sampling that has been done represents a tiny fraction of its total area. Whether the communities in unsampled areas are similar to or different from those in sampled areas, whether there are regions of unusual productivity or diversity that have not yet been found, whether the abyssal plain conceals large-scale ecological patterns that the current sampling density cannot reveal. These questions remain open. The ocean floor is not a uniform environment. It is a landscape of extraordinary diversity, vent fields and underwater mountains and deep plains and continental slopes and the deepest trenches, each with its own character, its own community of organisms, its own set of geological and chemical processes. What we have mapped and described represents, at best, a sketch of this landscape enough to see its major features, not enough to understand it. The details are missing. And in the details, as every biologist and geologist who has gone to look has found, the surprises are always waiting. We have been more surprised by the ocean floor, in the small fraction of it we have examined, than by anything we have found in space. Every major expedition to the deep ocean has returned with organisms or processes or geological features that were not predicted, not expected, not explicable within the framework that existed before the expedition went down. Space exploration has produced extraordinary discoveries, but the discoveries were, in most cases, the confirmation or extension of predictions made from existing theory. The ocean floor has not played by those rules. It has consistently shown us things we did not know to look for, and the part of it we have not yet looked at is vastly larger than the part we have. That fact, the vastness of what remains unknown, compared to the smallness of what we have seen, is what makes the ocean floor more mysterious than outer space. Not because space is less interesting, or because its mysteries are less profound, but because the mystery of the ocean floor is right here, on this planet, accessible in principle if not yet in practice, potentially holding answers to questions we have not yet thought to ask. The universe beyond Earth is enormous and strange and full of wonders, but the floor of our own ocean is already strange enough, already full of wonders enough, and we have barely begun to look. The numbers make this concrete in a way that resists comfortable abstraction. The ocean covers 362 million square kilometers. High-resolution mapping, the kind that reveals features at the scale of tens of meters, the kind that would allow a geologist or a biologist to actually understand the terrain, has been completed for roughly 20 to 25% of this area, depending on the definition of high resolution used. The rest has been mapped at the coarse resolution available from satellite altimetry, or not mapped at all in any systematic way. To put this in perspective, the area of the ocean floor that remains to be mapped at high resolution is roughly equivalent to 3 times the total land area of Earth. We're talking about an unexplored terrain larger than Africa, Europe, Asia, the Americas, and Australia combined. Not unexplored in the sense of never having been visited. Some of it has been sampled. Some of it has been photographed. Some of it has been crossed by research vessels collecting data. Unexplored in the sense that the detailed, systematic mapping that would allow us to say we actually know the terrain has not been done. The comparison with Mars becomes even more striking when you consider what high-resolution mapping has revealed in the small fraction of the ocean floor where it has been done. Every time researchers have gone to a new area of the seafloor with good instrumentation and looked carefully, they have found things that were not expected. New species, new geological formations, new chemical processes, new ecological communities, operating in ways that existing theory did not predict. The rate of discovery in the deep ocean per unit area sampled is higher than anywhere else on Earth, and the area remaining to be sampled is larger than any other unexplored environment on the planet. This is what makes the ocean floor more mysterious than Mars. Not that it is stranger or more alien, though in many ways it is, but that the ratio of what is unknown to what is known is higher here, on this planet, in this ocean, than on any world we have studied from afar. Mars has been mapped. Its major features are known. The surprises that await future exploration of Mars are the surprises of detail, the specific compositions of rocks, the precise history of a particular valley, the fine structure of atmospheric processes. The surprises that await exploration of the ocean floor are the surprises of entirely new phenomena, things that do not fit any existing framework, things that require new science to explain, things that change what we think we know. We have been surprised by the ocean floor, fundamentally and repeatedly every time we have gone to look. There is no reason to believe that the unlooked at portions are any different. They are simply waiting, patient, dark, pressurized, full of things we have not yet imagined. The ocean floor is the largest unexplored territory on Earth, and the most likely place on this planet to contain something we have never seen before. The question is not whether there are things down there worth finding. The history of ocean floor exploration has settled that question conclusively. The question is when we will go looking with the seriousness, the resources, and the systematic intention that the task deserves. The ocean floor will not come to us. We have to go to it. And most of it, even now, is still waiting for someone to arrive. The vacuum of space is, in engineering terms, a more forgiving environment than the deep ocean. This is counterintuitive. Space is lethal to unprotected humans in seconds. The absence of pressure causes blood to boil. The absence of oxygen causes immediate loss of consciousness. The temperature extremes of direct sunlight and shadow can swing hundreds of degrees within minutes. Space feels hostile in a way that the ocean does not. You cannot walk out into space without dying. You can walk into the ocean, at least at the surface, without any equipment at all. But the engineering challenge is not about what kills an unprotected human. It is about what a vehicle must withstand to operate reliably in a given environment. And by that measure, space is genuinely easier than the deep ocean. Not slightly easier, but fundamentally, categorically easier, in ways that explain much of why we have explored space more thoroughly than we have explored the depths beneath our own feet. The core of the problem is pressure. In space, the pressure outside a spacecraft is essentially zero, a hard vacuum. The pressure inside a crewed spacecraft is maintained at roughly 1 atmosphere, the same as sea level on Earth. The pressure differential between inside and outside is 1 atmosphere. The spacecraft hull must be strong enough to contain 1 atmosphere of pressure against a surrounding vacuum. This is not trivial engineering. Spacecraft must be carefully sealed. Their structures must withstand vibration and thermal stress, and any breach of the hull is immediately dangerous. But 1 atmosphere of pressure differential is a manageable engineering challenge. The materials, science, required to build a hull that contains 1 atmosphere against a vacuum has been understood and practiced for decades. In the deep ocean, the situation is inverted and amplified. A crewed submersible operating at 1,000 meters depth faces an external pressure of approximately 100 atmospheres, 100 times the pressure inside the vehicle. At 4,000 meters, 400 atmospheres. At the bottom of the deepest ocean trenches, over 1,000 atmospheres. The pressure differential between inside and outside is not one atmosphere pushing outward against nothing. It is 100, 400, or 1,000 atmospheres pushing inward against the vehicle's structure. The hull must resist crushing rather than bursting. And the engineering challenge of resisting 1,000 atmospheres of compressive force on a structure that must also be light enough to maneuver, transparent enough in at least some spots to allow observation, and penetrable by cables and hydraulic systems without leaking this is a substantially harder problem than building a hull that contains one atmosphere against a vacuum. The physics of this difference are worth dwelling on. In space, a spacecraft hull that develops a small crack or pinhole leak loses pressure slowly. The crew has time to respond, to seal the breach, to take corrective action. The consequences of small failures are serious, but not necessarily immediately fatal. In the deep ocean, a hull that develops a small crack at significant depth does not merely allow water to trickle in. It undergoes catastrophic implosion. The enormous pressure differential between the high pressure outside and the low pressure interior drives the water through any breach with enormous force, and the structural failure propagates essentially instantaneously across the entire hull. There is no slow leak, no warning, no time to respond. A small structural failure in a deep-sea submersible at depth is, by the nature of the physics, a total failure. This is why the design of crewed deep-sea vehicles has always centered on the pressure sphere, a geometrically perfect sphere of thick material, because a sphere is the optimal shape for resisting uniform compressive force. The sphere distributes the compressive load evenly across its entire surface, minimizing stress concentrations. Every deviation from perfect sphericity is a potential point of failure, because the pressure differential is too large to tolerate imperfection. The fabrication of pressure spheres for crewed deep-sea vehicles requires machining to tolerances that are difficult to achieve and verify, using materials, titanium alloys, specialized steels, acrylic composites for viewports whose behavior under sustained high pressure must be known with great precision. A crewed spacecraft, by contrast, is not constrained to any particular geometric form. It can be roughly cylindrical, roughly conical, roughly whatever shape is aerodynamically and structurally appropriate for its mission. The International Space Station is an irregular assembly of modules connected at various angles, a shape that would be catastrophic in the deep ocean, because the connections between modules would be sites of structural weakness under high compressive pressure. In space, those connections are fine, because the pressure differential they must withstand is only 1 atmosphere. Beyond the pressure problem, there is the problem of communication. Radio waves travel through space with minimal loss. A spacecraft, billions of kilometers away, like the Voyager probes, now beyond the solar system, can still communicate with Earth, its signals propagating through the vacuum at the speed of light, weakened by distance, but still detectable by large antennas. The communication infrastructure for space exploration is essentially free. You send radio signals, they travel, they arrive. The distances involved introduce time delays, but the signals themselves propagate reliably. Radio waves do not propagate through seawater. Seawater is electrically conductive, and electrical conductivity absorbs electromagnetic radiation, the same physical principle that makes it impossible to image the seafloor from orbit. Also prevents conventional radio communication with underwater vehicles. Seawater is electrically conductive, and electrical conductivity absorbs electromagnetic radiation. Radio waves are attenuated to nothing within a few meters of the ocean surface. Communicating with a vehicle operating at depth requires either physical tethers, cables that carry signals between the vehicle and the surface, or acoustic communication, which uses sound waves rather than electromagnetic waves and can propagate through water over considerable distances. Acoustic communication works, but it is slow, limited in bandwidth, and subject to interference from the complex acoustic environment of the ocean. The speed of sound in water is roughly 1,500 meters per second. A vehicle operating at 3 kilometers depth, communicating acoustically with a surface ship, experiences a 2-second round-trip delay in every exchange. This is manageable for simple commands and status updates, but makes real-time video transmission and complex operational coordination much harder than radio communication allows in space. The bandwidth available through acoustic links is a fraction of what radio links in space can provide. Transmitting high-definition video from a deep-sea vehicle to the surface in real time requires either a physical tether or technologies that are still under development. The implication is that deep-sea vehicles operating without tethers, autonomous underwater vehicles, must be substantially more capable of independent decision-making than their space equivalents, because they cannot rely on continuous high-bandwidth communication with operators at the surface. An autonomous vehicle on the seafloor, operating on acoustic communication alone, is more isolated from human guidance than a spacecraft in orbit around Mars. The operational autonomy required to conduct useful scientific work in the deep ocean is, in some respects, more demanding than the autonomy required for space missions, despite the fact that the deep ocean is a few kilometers away rather than tens of millions of kilometers. Then there is the problem of power. Spacecraft in the inner solar system within roughly the orbit of Jupiter can use solar panels to generate electricity. The sun's light is available continuously. The photovoltaic technology is mature, and a well-designed solar array can power a spacecraft's instruments and communications for years or decades. For deep-sea vehicles, solar power is irrelevant. The ocean absorbs sunlight within the first few hundred meters, and vehicles operating in the deep ocean receive no solar input at all. They must carry their power with them in the form of batteries or receive it through tethers from the surface. Battery technology constrains the endurance of untethered deep-sea vehicles in ways that have no equivalent in space. A spacecraft can operate continuously for decades on solar power. An autonomous underwater vehicle operating on batteries has a limited endurance measured in hours or days before it must return to the surface or a charging station to replenish its power. This limits the range and duration of operations, and it means that covering large areas of the seafloor requires either many vehicles operating simultaneously or repeated deployments of the same vehicle, both of which add to the cost and logistical complexity of deep ocean. Research. The combination of pressure, communication, and power constraints means that designing and operating a vehicle capable of conducting sustained scientific work in the deep ocean is, in several technical respects, harder than designing and operating a spacecraft capable of conducting sustained scientific work in orbit. This is not a statement that space exploration is easy. It is not. But the specific technical challenges of the deep ocean are different from, and in some ways more demanding than, the technical challenges of space, despite the vast difference in physical distance. Why, then, has space exploration attracted so much more investment? The answer is not purely technical. It involves history, culture, politics, and the particular way that human beings respond to visible achievement. The space race of the 1950s and 1960s was driven by geopolitical competition between the United States and the Soviet Union, a competition in which visible, dramatic achievements carried enormous symbolic weight. Landing a human on the moon was a statement about national capability and ideological superiority that no amount of deep ocean exploration could match, because the moon was visible in the sky every night and the ocean floor was invisible beneath a featureless surface. The investments made during the space race created infrastructure launch facilities, spacecraft manufacturing capabilities, training programs, scientific institutions that persisted after the race itself ended and continued to attract funding and talent. Space exploration had momentum, institutional weight, and a cultural visibility that deep ocean exploration never achieved. The astronaut became a cultural icon. The oceanographer did not. The imagery of space, the photographs of Earth from orbit, the footage of astronauts walking on the moon, the images of distant planets returned by space probes captured public imagination in ways that the imagery of the deep ocean, which required specialized equipment to obtain and showed strange organisms in featureless darkness, did not. This cultural asymmetry has had real consequences. Space agencies have received funding that ocean research programs have not. The best engineers and physicists of several generations were drawn to space by the prestige and resources that space exploration offered. The technologies developed for space exploration, miniaturization, precision manufacturing, material science have benefited space exploration enormously, while comparable investment in the technologies needed for deep ocean exploration has been much slower to arrive. The irony is that the technologies now becoming available, better autonomous vehicles, improved battery systems, cheaper and more capable sensors are beginning to make deep ocean exploration more feasible at the same moment that the scientific community is becoming more aware of how important the ocean floor is to the functioning planet. The window of opportunity is opening slowly as the tools improve and the understanding of what is at stake grows. What has not yet arrived, in the proportion that the task requires, is the will to match the technology with the investment. The ocean floor is the last great unexplored environment on this planet. Whether it will be explored before the changes now underway alter it irreversibly is a question that the next few decades will answer. There is one more dimension of the technical asymmetry that deserves attention because it shapes not just the cost of deep ocean exploration, but the experience of doing it. The phenomenology of being in the deep ocean compared to being in space. Astronauts in orbit can look out the window and see the Earth below them, the curve of the planet, the blackness of space. The view from orbit is legible. You can see where you are, orient yourself relative to familiar references, develop an intuitive understanding of your position in three-dimensional space. The environment is dark and cold and lethal outside the spacecraft, but it is visually comprehensible. In a deep-sea submersible, the view from the viewport reveals essentially nothing at distances greater than a few meters. The lights of the vehicle illuminate a small sphere of water, and whatever happens to be within it, the sea floor, if you are near it, or simply dark water, if you are descending. Outside that sphere of light, there is nothing. No reference, no horizon, no ambient illumination, no visual cue of any kind. Pilots of deep-sea submersibles navigate primarily by instruments, by depth gauges, by acoustic positioning systems, by sonar displays that show the bottom as a pattern of returns rather than as something you can see. The environment is opaque in a way that space is not. Space, paradoxically, offers more visibility than the ocean. This opacity shapes how science is done in the deep ocean. Observations are limited to what the vehicle's lights and cameras can capture within a small radius. Context: the relationship between a specific observation and its surroundings must be reconstructed from acoustic mapping and navigation data rather than direct visual assessment. A geologist on the Martian surface, with its thin but transparent atmosphere, can look across kilometers of terrain and orient observations within a visual landscape. A geologist on the ocean floor can see a few meters of seafloor and must infer everything beyond that radius from instruments. The combination of depth, pressure, communication constraints, power limitations, and visual opacity means that the ocean floor is, in operational terms, one of the most challenging environments on Earth for sustained scientific work. Not the most dangerous with proper engineering. Deep-sea vehicles are remarkably reliable, but the most technically demanding in terms of the infrastructure and expertise required to conduct useful research there. Every hour of science on the ocean floor is the product of months of preparation, specialized equipment, and substantial financial investment. The ratio of science produced to resources invested is lower in the deep ocean than almost anywhere else on Earth. This is changing. The development of lower-cost autonomous underwater vehicles that can be deployed without the support of expensive research ships that can operate for days or weeks on battery power, that can collect data and return to the surface without human intervention, is beginning to make deep ocean exploration more accessible. The development of better sensors, better battery technology, better acoustic communication systems, and better navigation algorithms is steadily improving the capability and reducing the cost of autonomous operation in the deep ocean. The ocean floor that was, a generation ago, accessible only to the most lavishly equipped research programs is becoming gradually accessible to smaller institutions and even to commercial operators. But the fundamental physics has not changed. The pressure is still enormous. The communication is still limited. The visibility is still essentially zero. The engineering challenge of operating reliably in the deep ocean remains one of the hardest problems in applied physics and material science. The ocean floor is becoming more accessible, slowly, incrementally, at the cost of sustained investment in technology. It is not becoming easy. It will not become easy. The deep ocean will always demand more of the vehicles and the researchers that enter it than any environment on this planet's surface, and more, in some technical respects, than the environment of space itself. Understanding this helps explain the knowledge gap that the previous section described, the gap between what we know about the surfaces of other worlds and what we know about the floor of our own ocean. The gap is not the product of indifference or irrationality. It reflects a genuine engineering challenge that has constrained how quickly the ocean floor can be explored, and a genuine cultural and institutional history that directed resources towards space at a time when the importance of the ocean floor was less well understood than it is now. What has changed is the understanding. We know more now about what the ocean floor does, how it regulates climate, how it sustains biodiversity, how it influences the chemistry of the ocean and the atmosphere, than we did when the decisions were made to invest in space exploration rather than ocean exploration. The case for systematic, well-funded, sustained exploration of the ocean floor is stronger now than it has ever been. Whether the institutions and the funding will follow the understanding, whether the case will be made and heard in time to matter, is a question that the coming decades will answer. The ocean floor is not asking us to explore it. It does not need us. But we need it to understand what it does, to protect what it contains, to learn what it can teach us about the planet and about life. And we need to go there with the seriousness that the task deserves, equipped with the knowledge that the environment is harder than space in some ways that matter, and armed with the technology that is, for the first time in history, beginning to be adequate to the challenge. Every year, scientists formally describe and name approximately 18,000 new species organisms that have never previously been recorded in the scientific literature, never given a Latin binomial, never placed in the tree of life. This sounds like a lot. It is not. The estimate of how many species currently exist on Earth ranges from 8 million to over 1 trillion, depending on whether you include microbial life. Even at the conservative end of that range, the roughly 2 million species currently described by science represent a small fraction of what exists. Most of life on Earth has never been named. Most of it has never been seen, and a disproportionate share of the unknown is in the ocean, specifically in the deep ocean, where the sampling has been most sparse and the organisms most remote from the scientists who study them. The Hadal Zone is the least known biological environment on Earth. This is the zone of the ocean below 6,000 meters. The depths found only in the deep trenches, the places where tectonic plates plunge downward and the ocean floor drops to its greatest depths. There are 27 major Hadal trenches in the world's oceans, scattered across all ocean basins. The total area of the Hadal Zone, the combined floor area of all the world's trenches at depths below 6,000 meters is less than the area of Australia. It is a small environment by ocean standards. And it is, in terms of biological knowledge, almost entirely uncharacterized. What biology does at Hadal depths is, in broad outline, known. The organisms that live there, bacteria, archaea, small crustaceans called amphipods, polychaete worms, holothurians, have been collected and described from a handful of locations. The basic fact of Hadal life, that organisms exist and function at pressures exceeding 600 atmospheres in complete darkness at temperatures near freezing, has been established. But the specific organisms that live in each individual trench, the ecological relationships between them, the degree to which trench communities are connected to each other or isolated by the vast, flat ocean floor that separates them. These questions have barely been asked, let alone answered. The reason is sampling. Collecting organisms from Hadal depths requires deploying equipment to depths of 6 to 11 kilometers and recovering it, which is technically demanding and expensive. The number of Hadal sampling expeditions conducted by the global scientific community over the past century can be counted in the hundreds, an extraordinary scarcity of data for an environment that, while small, is biologically distinct and contains organisms not found anywhere else on Earth. Many of the world's Hadal trenches have been sampled once, or not at all. The biological communities in those trenches are unknown in every meaningful sense of the word. What is known from the trenches that have been sampled suggests that Hadal biology is more interesting than expected. The amphipods that dominate the Hadal megafaunal community, small crustaceans, typically a few centimeters long at the surface, reaching extraordinary sizes in the Hadal zone, a manifestation of the deep-sea gigantism that characterizes many deep-sea lineages, have been found in every trench sampled. But the specific species differ from trench to trench. The Mariana Trench has its amphipods. The Kermadec Trench in the South Pacific has different amphipods. The Izu Ogasawara Trench off Japan has others. The Hadal trenches, separated by thousands of kilometers of deep ocean floor at shallower depths, appear to be biologically isolated from each other, each a distinct biological province, with its own community of organisms shaped by its particular geological history and oceanographic context. The degree of endemism in Hadal communities, the fraction of species found in one trench but not in others, is poorly known but appears to be high. If each trench harbors organisms found nowhere else, then the total biological diversity of the Hadal zone is much greater than the diversity of any individual trench would suggest. And if most trenches have never been sampled, the total unknown diversity of the Hadal zone is correspondingly large. The trenches are not merely extreme environments where the same handful of adapted organisms scrape out a living. They may be hotspots of biological diversity, each a unique evolutionary experiment conducted in isolation over millions of years. Below the organisms visible to the naked eye, the sediment of the Hadal zone contains microbial communities of extraordinary density and activity. This was not expected. The conventional understanding was that the deep ocean sediment becomes progressively more sterile with depth that the high pressure, low temperature, and limited energy supply of the deep ocean would reduce microbial activity to negligible levels. The measurements made in hadal sediment samples have challenged this understanding. Microbial cell counts in the sediment of deep trenches are often higher than on the surrounding deep sea floor, not lower. The trenches accumulate organic matter delivered by currents that funnel material from the surrounding ocean floor into the trench axis, and this organic matter supports microbial communities that are, in some trenches, more active than the microbial communities of some surface soils. The microbes of the hadal sediment are not merely living, they are processing organic matter, cycling nutrients, performing chemical transformations that influence the chemistry of the overlying water column. The hadal zone, which constitutes a tiny fraction of the ocean floor by area, may be disproportionately important as a site of organic matter processing and nutrient cycling, a conclusion that would not have been anticipated from the conventional understanding of deep-sea biology, and that remains to be fully tested across the global hadal system. Away from the trenches, on the continental slopes and margins, the ocean floor transitions between the relatively well-studied shallow coastal environment and the poorly known deep ocean. The continental slope, the steeply inclined terrain that drops from the shallow continental shelf to the deep ocean floor, is one of the most topographically varied environments in the ocean, and one of the least studied. Cold seeps are among the most remarkable features of the continental slope, and they illustrate how much of the ocean floor's complexity remains undiscovered. Cold seeps are places where hydrocarbon-rich fluids, primarily methane and hydrogen sulfide, leak from the seafloor, driven by the compression of organic-rich sediments in the geological structures of the continental margin. Unlike hydrothermal vents, which are powered by geological heat, cold seeps operate at ambient deep ocean temperatures. The fluids they release are not hot. They are the same temperature as the surrounding water, but they are chemically rich, and the organisms that have evolved to exploit them are, in many respects, as remarkable as the organisms of hydrothermal vents. Cold seep communities are anchored by chemosynthetic bacteria and archaea that oxidize methane and hydrogen sulfide to produce organic matter supporting food webs that operate independently of the surface ocean's productivity. The mussels and clams of cold seep communities, many of them related to but distinct from the organisms of hydrothermal vents, harbor chemosynthetic bacteria in their tissues. Tube worms, often belonging to different species than the vent tube worms but performing the same ecological function, colonize the areas of most active seepage. The communities that form around cold seeps can be dense, productive, and biologically diverse, despite being located on a continental slope that, between seep sites, supports only a sparse fauna. Cold seeps have been found on continental slopes in every ocean. The total number of cold seep communities is unknown, because finding them requires surveying the seafloor with instruments capable of detecting the chemical signatures of seepage, water column anomalies in methane concentration, characteristic acoustic backscatter signatures on sonar surveys, or the direct observation of seep fauna from remotely operated vehicles. Systematic surveys of this kind have been conducted along some continental margins: the Atlantic margin of North America, parts of the Pacific margin, portions of the Arctic continental shelf, but large areas of the global continental slope have not been surveyed for cold seep activity. Unknown numbers of cold seep communities exist in these unsurveyed areas. The methane associated with cold seeps is not merely a chemical curiosity. It is stored in the continental margins in enormous quantities, primarily in the form of methane hydrate, a crystalline structure in which methane molecules are trapped within a lattice of water molecules, stable at the temperatures and pressures of the deep sea, but unstable if conditions change. The global inventory of methane hydrate, the total amount of methane stored in this form in the world's ocean sediments, is estimated to be enormous, potentially containing more carbon than all other known fossil fuel reserves combined. Whether and how this methane could be released into the ocean and atmosphere as the deep ocean warms is one of the major uncertainties in climate projections, and understanding it requires knowing far more about the distribution and character of methane hydrate deposits than current surveys have established. The manganese nodules of the deep ocean floor represent a different kind of unexplored resource. These are potato-shaped concretions of manganese dioxide and other metal oxides, nickel, cobalt, copper, that form slowly on the seafloor over millions of years, accumulating at rates of millimeters per million years as metals precipitate from seawater onto nucleating particles. The polymetallic nodules, as they are formally known, cover vast areas of the deep ocean floor, particularly in the Clarion-Clipperton zone of the equatorial Pacific, where they occur in densities of tens of kilograms per square meter over millions of square kilometers. The metals in these nodules, manganese, nickel, cobalt, copper, and rare earth elements, are the same metals required for the batteries and electronics that underpin the global transition to renewable energy. The demand for these metals is expected to increase dramatically as electric vehicle production scales and energy storage requirements grow. The nodules of the deep ocean represent a potentially enormous source of these critical materials, and commercial interest in deep-sea mining has grown substantially in recent years. But the nodules also support biological communities. The hard substrate of the nodule surface, rare on the soft sediment deep ocean floor, provides attachment points for organisms that require hard substrate sponges, corals, cnidarians, bryozoans, and other sessile organisms that cannot live on soft sediment. The nodule fields are, in a biological sense, reef-like environments in a habitat otherwise dominated by soft sediment. Their removal from mining would destroy not just the nodules, but the communities that live on them, communities that, like those of the Haddle Trenches, are poorly characterized and may contain large numbers of undescribed species. The biological surveys of nodule field communities conducted before the current wave of commercial interest found diverse and apparently endemic fauna's organisms that appeared to be restricted to nodule habitats, not found elsewhere on the seafloor. Whether these organisms are truly endemic or simply rare elsewhere is not known. Whether the nodule communities recover after disturbance, whether the organisms that live on the nodules can recolonize after the nodules are removed is also not known. Recovery experiments conducted in areas disturbed by dredging decades ago suggest that recovery, if it occurs, is extremely slow, consistent with the slow metabolic rates and long generation times of deep-sea organisms, but raising serious questions about whether mining disturbance is effectively permanent on any human timescale. The ocean floor contains, in its cold and dark expanse, more geological and biological complexity than any map we currently have is capable of showing. Every environment on the ocean floor, the Hadal trenches, the cold seeps, the nodule fields, the continental slopes, the volcanic structures of the underwater ridge systems, is a world unto itself, with its own community of organisms, its own set of geological processes, its own chemical environment, its own evolutionary history. Understanding the ocean floor means understanding all of these environments separately and in relation to each other. It means knowing not just that they exist, but how they function, how they are connected, how they respond to perturbation, and how they contribute to the overall functioning of the ocean as a planetary system. That understanding does not exist. It cannot exist until more of the ocean floor has been observed directly, sampled systematically, and studied with the care and resources that the task demands. The organisms and processes waiting to be found in the unexplored portions of the ocean floor are not hypothetical. They are real. They are there now, in the dark, doing what they have always done. The question is whether we will go to find them before other forces, the warming of the deep ocean, the acidification of the water, the disruption of the seabed by mining, alter or eliminate them before science has had the chance to understand what they are. The scale of what remains unknown becomes clearer when you consider specific numbers. Marine taxonomists, the scientists who describe and name new ocean species, estimate that between 500,000 and 10 million species live in the ocean, most of them in the deep sea. The number currently described is roughly 250,000. Even at the conservative end of the estimate, the described species represent less than half of what exists. At the upper end, the described species are less than 5% of the total. Every expedition to the deep sea returns with specimens that cannot be matched to any described species. In some taxonomic groups, nematodes, polychaetes, copepods, foraminifera, the rate of new species discovery from deep-sea samples approaches 100%. Almost everything collected is new to science. This rate of discovery is itself evidence of how poorly the deep sea has been sampled. In environments that have been thoroughly surveyed, the birds of North America, the mammals of Europe, the flowering plants of the British Isles' new species are rarely found. The baseline is known. The inventory is essentially complete. In the deep sea, every systematic sampling effort returns new species, which means the inventory is far from complete, and the sampling has been far too sparse to approach completeness. The deep ocean is not merely unexplored in the geographic sense. It is unexplored in the biological sense, to a degree that has no equivalent in any other large environment on Earth. The geological dimension of this ignorance is equally striking. The topography of the ocean floor, the three-dimensional shape of the terrain, contains features that are not yet cataloged. The global inventory of submarine volcanoes is incomplete. The total number of hydrothermal vent fields is unknown. The distribution of cold seep systems across the global continental margins has not been systematically mapped. The internal structure of the sediment layers that cover the ocean floor, the record of geological and biological history preserved in those layers, has been sampled at only a few thousand locations across the entire ocean basin. Each core of ocean sediment is a record of history, a column of material deposited over thousands or millions of years, preserving in its chemistry and its fossils the conditions that prevailed when each layer was laid down. The temperature of the ocean, the circulation patterns of the water, the productivity of the surface ecosystem, the concentration of greenhouse gases in the atmosphere, all of these leave signatures in the sediment record. The sediment cores recovered by scientific drilling programs have produced some of the most important data in climate science, providing the long-term context against which current climate change is understood. But the cores come from a small number of locations. The spatial variability in the sediment record the differences between one location and another that reflect regional oceanographic history remains poorly constrained. Understanding the ocean floor, in the fullest sense, means understanding not just what lives there now, but what has lived there in the past. Not just the current topography, but the geological history that produced it. Not just the current chemistry, but the biogeochemical processes that have shaped the ocean over millions of years. The ocean floor is not merely a present-tense environment to be described. It is a record, a deep-time archive of the history of the ocean and the atmosphere and the climate that is encoded in the sediment and the rock and the chemistry of the water that flows through it. Most of that archive has never been read. The instruments that could read it, the drills and the cores and the sensors and the sampling systems, have visited a tiny fraction of the ocean floor. The rest of the record is intact, preserved in the cold and the dark, waiting for the tools and the will to retrieve it. What it would tell us about the history of the planet, about the long-term behavior of the climate system, about the past abundances and distributions of species that are now rare or extinct, is unknown, because the archive itself is largely unread. This is what the ocean floor contains. Not just organisms that are strange and interesting in themselves, not just geological features that are remarkable on their own terms. It contains the history of the planet, written in sediment and chemistry, accessible in principle to anyone with the instruments to read it. It is the deepest and most comprehensive archive of Earth's past that exists anywhere on this planet, and we have barely opened it. There is a category of ignorance that is more profound than ordinary not knowing. Ordinary not knowing has a shape. A scientist who does not know the population size of a particular deep-sea species knows that this is something that could, in principle, be measured. The question exists, the answer is absent. The gap between question and answer is recognized and can be worked toward. This kind of ignorance is uncomfortable, but manageable. It is the normal condition of science at any frontier. You know what you do not know, and you can design studies to find out. The deeper ignorance is different. It is the ignorance of questions that have not yet been formulated, of phenomena that have not yet been detected, of categories of existence that have not yet been conceived. You cannot ask a question about something you do not know exists. You cannot design a study to investigate a phenomenon you have no reason to suspect is there. This kind of ignorance does not feel like ignorance from the inside, because there is no awareness of the gap. It feels like completeness. It feels like a satisfactory understanding of the way things are. And it persists, invisibly, until something unexpected breaks through the framework and forces a revision. The history of ocean floor science is, in substantial part, a history of this deeper ignorance being repeatedly breached, not gradually, not through the slow accumulation of anomalies that eventually demanded explanation, but through specific moments of discovery in which something that should not have been there by the standards of everything previously known turned out to be there. These moments did not merely add new information to existing frameworks. They required the frameworks themselves to be rebuilt. The transformation of our understanding of how life obtains energy is the most dramatic example, but it is not the only one. The discovery that the ocean floor is geologically active, that new ocean floor is continuously being created as spreading centers and consumed as subduction zones, and that this process is the engine of continental drift and mountain building, and the long-term cycling of carbon between the ocean and the atmosphere was a conceptual revolution of the first order. Before the theory of plate tectonics was accepted in the mid-20th century, the ocean floor was thought to be geologically inert, the permanent basement of the ocean, stable and unchanging, a passive surface on which marine sediments accumulated. The data that overturned this understanding came largely from the ocean floor itself, from magnetic anomaly surveys and seismic studies, and eventually from direct observation by submersibles. The framework was not modified, it was replaced. The replacement of geological frameworks is now history, and its lessons seem obvious in retrospect. Of course, the ocean floor is dynamic. Of course, new crust is being created, and old crust consumed. The evidence, once collected, is overwhelming. But before the evidence was collected, the framework was wrong, and the wrongness was invisible because no one had the data to see it. The scientists who believed the ocean floor was geologically inert were not foolish or careless. They were working with the best available information and constructing the most coherent framework that information supported. The framework was wrong because the information was incomplete. The same pattern has repeated in biology. The discovery that the ocean sediment contains vast microbial communities, living organisms present in every sample taken from the deep seafloor, at densities that, while low compared to surface environments, represent an enormous total biomass when integrated over the entire ocean floor, was not anticipated. The prevailing understanding was that life became increasingly sparse and eventually negligible at great depths. What the sampling revealed was that life is present everywhere in the ocean sediment, to depths of hundreds of meters below the seafloor, in conditions of vanishingly small energy supply and geological pressure. Alive in the most technical sense, but operating at metabolic rates so low that they challenge the definitions of what being alive means. The deep subsurface biosphere, the community of organisms living in the rock and sediment beneath the ocean floor, not just on its surface, is now estimated to contain a biomass comparable to or exceeding the biomass of all life on the surface of the land. This estimate is deeply uncertain. The sampling is too sparse, and the organisms too difficult to count precisely for confident quantification. but even the lower bounds are staggering. There may be as much living material in the rocks beneath the ocean floor as in all the forests and grasslands and agricultural lands of the continents combined. This was not known 20 years ago. It was not suspected. It was not a hypothesis waiting for confirmation. It was simply absent from the framework, a phenomenon so unexpected in an environment so remote from ordinary biological intuition that no one had thought to look for it until the technology to look became available. And when they looked, they found it, and the framework had to expand to accommodate it. The lesson is not merely that the ocean floor contains surprises. Every unexplored environment contains surprises. The lesson is about the nature of scientific frameworks and their relationship to evidence, about how the questions we ask are shaped by the frameworks we hold, and how the frameworks we hold are shaped by the evidence we have collected, and how incomplete evidence produces frameworks that feel complete from the inside but are not. The ocean floor has provided, repeatedly, evidence of phenomena that did not fit the frameworks in place when the evidence arrived. The response of science to this evidence has been to revise the framework slowly at first, then more rapidly as the evidence accumulated, until the revision was complete and the new framework was established. But each revision has produced a new framework that is, in turn, incomplete in ways that are not yet visible, because the evidence that would reveal the incompleteness has not yet been collected. The ocean floor still holds, in its unexplored depths, phenomena that do not fit the frameworks we currently hold. We do not know what they are, because if we knew what they were, they would already be in the framework. This epistemological situation is not unique to ocean science. Every scientific frontier has the same character. What is distinctive about the ocean floor is the scale of the unexplored territory and the rate at which exploration has returned unexpected findings. In environments where the sampling has been dense and systematic, where many observers have gone to many locations and looked carefully, the frameworks have had time to stabilize and be tested. Anomalies are detected and investigated. The frameworks evolve continuously, but without dramatic rupture. In the ocean floor, where the sampling has been sparse and geographically limited, the frameworks have not had the opportunity to be tested against the full diversity of what exists. They are extrapolations from a small sample to a large whole, and the large whole contains things the small sample did not reveal. The history of science gives us reasons to expect that the unexplored portions of the ocean floor will contain phenomena that the current framework does not accommodate. Not one such phenomena, but several. Not small anomalies that require modest revision, but category errors, misclassifications of fundamental importance, missing principles, absent mechanisms that, when discovered, will require rebuilding portions of the framework rather than merely adjusting its parameters. This expectation is not mystical or romantic. It is an inference from pattern. Every time the ocean floor has been explored with new tools or in new locations, it has returned findings that exceeded the framework. The pattern has been consistent across 60 years of systematic deep ocean research. The tools have improved. The locations explored have expanded. The findings have continued to exceed expectations. There's no reason to believe that the unexplored portions are different from the explored ones in this respect. No reason to believe that the portions we have not yet visited will, when visited, turn out to be exactly what the current framework predicts. The ocean floor will surprise us again. The question is not whether, but when and how. And the answer depends on when and how we go looking, with what tools, in what locations, asking what questions. The questions we ask shape what we are capable of finding. Questions formed within the current framework will find answers that refine the framework. Questions that exceed the framework, that probe phenomena the framework does not yet recognize, require going to the ocean floor without predetermined expectations, collecting data comprehensively rather than selectively, and allowing the data to suggest questions that the framework did not anticipate. This is a different mode of science than the hypothesis-driven research that dominates most modern scientific practice. Hypothesis-driven research is efficient. It focuses resources on specific questions and produces specific answers. It is the right approach when the framework is well developed and the questions are clearly formulated. It is not sufficient when the framework is incomplete, and the most important questions are the ones that have not yet been asked. The ocean floor requires both modes: hypothesis-driven research to refine and extend the current framework, and exploratory research to find what the framework does not predict. The balance between the two has, historically, been tilted strongly toward hypothesis-driven work, toward expeditions designed to answer specific questions, rather than expeditions designed to look broadly and see what is there. The result is a body of knowledge that is deep in some areas and entirely absent in others, shaped more by what scientists had reasons to look for than by what the ocean floor actually contains. What the ocean floor actually contains in its entirety, across all of its vast and varied terrain, remains unknown. The known portions are remarkable. The unknown portions are vast. And somewhere in the unknown, there are things that will require the framework to be rebuilt again, phenomena that are there right now, in the cold and the dark, doing what they have always done, invisible to science, only because science has not yet gone to look. There is something both humbling and exhilarating about this. Humbling because it means that the understanding we have is incomplete in ways we cannot see, that the map we have drawn of ocean floor science has blank spaces, not just in the regions we have not visited, but in the conceptual territory we have not yet conceived. Exhilarating because it means the future holds discoveries of the kind that happened in 1977, when the lights of a submersible illuminated something that should not have been there, and the world of biology was permanently changed. Those discoveries are waiting. They have always been waiting. The deep ocean is patient in ways that science, with its funding cycles and publication pressures and career timelines, often is not. The question is whether the science will become patient enough to match the ocean, to commit to the long, systematic, comprehensive exploration that the task demands, and to remain open to finding what the framework does not predict, rather than only what it does. The concept of absent knowledge, knowledge that does not exist because the questions that would generate it have not been asked, has a practical consequence for how we assess what we know about the ocean floor. When we say that we have explored 20 or 25% of the ocean floor at meaningful resolution, we are describing the geographic extent of our mapping. But mapping is only the most basic form of knowledge. Knowing the shape of the terrain is different from knowing what lives there. And knowing what lives there is different from knowing how it functions. And knowing how it functions is different from understanding its role in the larger systems, the ocean, the climate, the biogeochemical cycles of which it is a part. At each level of this hierarchy, the known fraction is smaller. The geographic coverage of mapping is 20 to 25%. The geographic coverage of biological sampling of expeditions that have actually collected organisms and studied the community structure is far smaller, perhaps a few percent of the ocean floor. The geographic coverage of ecological research, of studies that have followed communities over time, measured their responses to perturbation, characterized the functional roles of their constituent species is smaller still, concentrated at a handful of sites that have been returned to repeatedly because they are accessible and because they have already yielded interesting results. And below all of this, at the most fundamental level, is the knowledge of what the ocean floor does, how it contributes to planetary processes, how it influences the chemistry of the ocean, how its biological and geological activity connects to the systems that regulate climate and sustain life on Earth. This functional understanding is built on the ecological research, which is built on the biological sampling, which is built on the geographic mapping. At each step, the foundation is narrower than the floor it supports. The structure of ocean floor knowledge is, in this sense, an inverted pyramid, broad conclusions drawn from increasingly narrow foundations, dependent on evidence from a small and potentially unrepresentative sample of what exists. This is not a criticism of ocean science. It is a description of the inevitable situation of any science operating in an environment as large and as difficult to access as the deep ocean. But it has implications for how confidently we can speak about what the ocean floor does and what it contains. The confident statements that can be made that the ocean floor is biologically inhabited throughout, that hydrothermal activity occurs along the global ridge system, that sediment communities process organic matter and psychonutrients, are supported by direct evidence from locations that have been studied. The extrapolations from those locations to the global ocean floor are inferences, and inferences from sparse data in an environment of known heterogeneity are uncertain. The uncertainty matters because the ocean floor matters. It is not a curiosity at the margin of the Earth system. It is a major component of the carbon cycle, the nutrient cycle, the climate system. The rates at which it processes organic matter, sequesters carbon, exchanges heat and chemicals with the overlying ocean, these rates determine, in part, how the ocean behaves and how the climate responds to perturbation. Getting these rates wrong, extrapolating incorrectly from sparse samples to global totals, introduces errors into climate models and biogeochemical models that propagate through to projections of future change. The corrective is more data, more sampling from more locations, conducted more systematically, analyzed more comprehensively. The tools to collect this data are improving. The costs are declining. The scientific community is increasingly aware of the gaps and their consequences. What remains to be aligned is the funding, the sustained, substantial, patient investment in ocean floor research that the importance of the problem demands, and that has, historically, not materialized at the scale the task requires. Part of the reason for this persistent underfunding is the same cultural and institutional dynamic described earlier. Space exploration captures imagination in ways that ocean exploration does not. But part of it is also the nature of the knowledge gap itself. It is hard to make a compelling case for funding research into things you do not know exist. The discoveries that justify the investment can only be made after the investment is made, not before. The return on the investment is by definition unknown before the research is done. This is the fundamental challenge of exploratory science. Science that is not testing hypotheses, but looking for phenomena that have not yet been predicted, and it requires a different kind of institutional support than hypothesis-driven research receives. The case for that support, in the context of ocean floor research, rests on a simple argument from pattern. Every previous investment in systematic ocean floor exploration has returned discoveries that exceeded expectations, that revised frameworks, that generated new questions more numerous and more interesting than the questions they answered. The pattern is consistent. The unexplored portions of the ocean floor are vast. The reasonable expectation, based on the pattern, is that exploring them will continue to yield discoveries of comparable importance. Funding ocean floor exploration is not a bet on a specific outcome. It is a bet on a pattern, on the consistent tendency of the deep ocean to contain more than we thought, to do more than we knew, to surprise us with phenomena that require the framework to be rebuilt. That bet has paid off every time it has been placed. The question is whether it will be placed with the scale and the commitment that the size of the unexplored territory demands. The ocean floor is not going anywhere. Its secrets are patient, but the window in which those secrets can be discovered before other processes, warming, acidification, mining, changing circulation, alter the environment that contains them is finite. The unknown is large. The time to explore it is not unlimited. What lies in the unexplored portions of the ocean floor is, by definition, unknown. But what we know about the explored portions, what the pattern of discovery tells us about what exploration produces, gives us strong reasons to believe that it is important and strange, and more than we currently imagine. The deep ocean has never disappointed those who went to look with open questions and honest instruments. It has only ever exceeded what they brought with them. That is the best argument for going. And most of the ocean floor, even now, has not yet been gone to. The ocean floor is not peripheral to the functioning of this planet. It is central to it in ways that become clearer the more carefully you look, and that have consequences for everything that happens on the surface, for the climate, for the chemistry of the atmosphere, for the long-term habitability of the Earth. Carbon is the element around which this centrality is most directly apparent. The ocean absorbs carbon dioxide from the atmosphere, roughly a quarter of all human carbon emissions since industrialization have been taken up by the ocean, slowing the rate of atmospheric warming considerably relative to what it would otherwise have been. this absorption is not passive. It is driven by biological and chemical processes in the ocean, and it ends, ultimately, on the ocean floor. When photosynthetic organisms in the surface ocean fix carbon dioxide into organic molecules, and those organisms die, and their remains sink through the water column, the carbon they contain is transported downward. Some of it is consumed and respired by organisms in the water column, releasing carbon dioxide back into the deep water. Some of it survives the descent and reaches the ocean floor, where it enters the sediment and is processed by the microbial communities that inhabit it. The fraction that is ultimately buried, incorporated into the sediment, and covered by subsequent layers, removed from contact with the ocean water above, is sequestered for thousands to millions of years. This burial of organic carbon is one of the mechanisms by which the ocean removes carbon from the active carbon cycle on geological timescales. The ocean floor is, in this sense, the endpoint of the process that makes the ocean a carbon sink. The efficiency of this endpoint, the fraction of organic carbon that reaches the floor and is buried, versus the fraction that is remineralized and returned to the water, determines how effective the ocean is at sequestering carbon over the long term. Changes in the deep ocean in its temperature, its circulation, its microbial communities alter this efficiency, and changes in this efficiency alter the rate at which carbon accumulates in the atmosphere. The deep ocean is warming. Not rapidly by surface standards, the heat content of the deep ocean increases slowly because the thermal inertia of a vast body of cold water is enormous, but measurably. The temperature of deep water has increased in parts of the ocean over the past several decades, driven by the circulation of surface-warmed water into the deep. As the deep ocean warms, the microbial communities that process organic carbon change warmer temperatures, accelerate metabolic rates, which means more carbon is respired and less is buried. The efficiency of the biological pump, already poorly understood, is being altered by a warming that is itself poorly constrained at depth. This is a feedback. Warming reduces carbon sequestration, which allows more carbon to accumulate in the atmosphere, which causes more warming, which further reduces carbon sequestration. The magnitude of this feedback depends on numbers we do not have on how much the deep ocean is warming, how microbial communities respond, how burial efficiency changes. These are empirical questions that require measurements that have not been made at the scale required to answer them confidently. The ocean floor, in its ignorance, introduces uncertainty into climate projections that could be reduced by better knowledge. The cost of that ignorance is not merely scientific, it is practical. Decisions about climate policy depend on projections that carry the uncertainty of the unknown ocean floor. The question of biodiversity and conservation is equally pressing. Conservation biology has developed sophisticated frameworks for protecting species and ecosystems, but those frameworks depend on knowing what exists, on having an inventory of the species and communities that need protection. You cannot protect what you do not know about. You cannot assess the conservation status of species that have never been described. You cannot identify critical habitats for protection if those habitats have never been surveyed. The ocean floor contains an unknown but potentially enormous fraction of Earth's total biodiversity. The communities on the underwater mountains, in the trenches, on the chemosynthetic seep fields, on the nodule-covered plains, all of these are inhabited by organisms that are, in most cases, either undescribed or so poorly known that their distribution and abundance cannot be assessed. Protecting these communities requires, as a minimum, knowing that they exist and where they are. The current state of knowledge does not meet that minimum for most of the ocean floor. The threats are real and accelerating. Deep sea bottom, trawling, the practice of dragging weighted nets across the seafloor to catch commercial fish and invertebrates, has already caused widespread damage to deep-sea coral and sponge communities on continental shelves and slopes around the world. The physical disturbance caused by a trawl net is severe. It destroys the three-dimensional structure of communities that have taken decades or centuries to develop, and recovery is slow to non-existent on any human timescale. The communities destroyed by trawling in many areas of the world, ocean have not recovered because the trawling has continued and the pressures have not been relieved. Deep-sea mining represents a new and potentially larger threat. The extraction of polymetallic nodules from the deep ocean floor, currently in the regulatory approval and environmental assessment phase in several jurisdictions, would disturb areas of seafloor measured in thousands of square kilometers per year if commercial operations proceed at the scale envisioned by the industry. The ecological communities of the nodule fields, poorly known but clearly inhabited by organisms with no other habitat, would be destroyed or severely damaged. The sediment plumes generated by mining operations would spread over areas far larger than the mining footprint itself, smothering organisms on the surrounding seafloor. And the time scale of recovery, given the long generation times and slow metabolic rates of deep-sea organisms, is measured in decades to centuries at minimum. The ethical dimension of this is straightforward. Destroying communities of organisms that have never been described, eliminating species that have never been named, before science has had the chance to understand what is being lost. This is a form of irreversibility that cannot be undone by subsequent regret. Once the nodule fields are mined, the communities that lived on them are gone. The organisms they contained, the evolutionary experiments they represented, the biological information they carried, this is permanently absent from the world. The fact that we did not know what was there does not diminish the loss. It compounds it. We will never know what we destroyed. Beyond climate and conservation, the ocean floor holds what may be the deepest question in biology. Where did life begin? The hypothesis that life originated at hydrothermal vents, that the first self-replicating chemistry emerged in the hot, chemically rich, sheltered environments of submarine volcanic systems, has gained substantial scientific support over the past 3 decades. The evidence is chemical. The reactions that are thought to have given rise to the first metabolic pathways are thermodynamically favorable at the temperatures and chemical conditions found at certain types of hydrothermal vents. The evidence is evolutionary. The deepest branches of the tree of life, the organisms most closely related to the last universal common ancestor of all living things, are thermophiles, organisms that thrive at high temperatures, of the kind found at hydrothermal systems. If life began at hydrothermal vents on the early Earth, then the ocean floor is not merely where much of life currently exists. It is where all life originated. The organisms that live there today, the chemosynthetic bacteria, the archaea of the hot springs, the ancient lineages of tube worms and clams are not merely exotic deep-sea fauna. They are the living descendants of the organisms that started everything. They are the representatives of the biochemical experiments that, billions of years ago, crossed the threshold from chemistry to biology. Understanding them in their natural context, in the environments that produced them, is not merely scientific curiosity. It is the study of our own origins. The same logic extends beyond Earth. If life originated at hydrothermal vents on this planet, and if similar vents exist on the icy moons of the outer solar system where liquid water and geological heat are present, where the same chemical conditions that gave rise to life here may be reproduced, then understanding deep-sea hydrothermal systems on Earth is the best preparation we have for finding life elsewhere. The biology of our own ocean floor is a model, the only model currently available, for what biology might look like in the subsurface oceans of worlds we have not yet visited. Learning it thoroughly before we go to those worlds is not merely valuable, it may be essential. The future of ocean floor exploration is beginning to take shape. Autonomous underwater vehicles are improving rapidly in endurance, in sensing capability, in navigational precision, in the ability to operate collaboratively as fleets rather than individually. The cost of deploying these vehicles is declining as manufacturing scales and the technology matures. The data they collect, acoustic surveys, water chemistry measurements, imagery, biological samples, can be processed by machine learning algorithms that can identify species, detect anomalies, and flag interesting features faster and more comprehensively than human analysts working alone. Within a generation, it may be possible to conduct a systematic biological survey of the entire ocean floor, not a complete characterization, which would require far more time and resources, but a reconnaissance that identifies the major habitat types, locates the most ecologically significant areas, and describes the broad outlines of the community composition across the global seafloor. This would be, by any measure, one of the most significant scientific undertakings in the history of biology. It would reveal, with confidence for the first time, what lives on the ocean floor of this planet. It would identify the habitats most in need of protection. It would locate the geological features most likely to harbor the most interesting biology. It would provide the baseline against which change can be measured. Whether this survey happens before the threats accelerate, before the mining proceeds, before the warming alters the communities that currently exist, this is not a scientific question. It is a question of priority, of resource allocation, of the degree to which the societies that have the technical capacity to conduct this survey choose to deploy it toward this purpose. The ocean floor does not know that it is unknown. It does not know that the species it contains have never been named, that the processes it sustains have never been fully characterized, that the history it records has never been read. It simply continues building its communities, cycling its chemistry, absorbing its carbon, preserving its sediment record, indifferent to whether anyone comes to look. But we know. We know that it is unknown, and we know that the knowledge matters, and we know that the window in which the knowledge can be obtained before the threats alter what is there to know is finite. What we do with that knowledge, how we act on it, how seriously we take the obligation to understand the largest environment on our own planet before we lose the opportunity, this is a choice that belongs to us and to no one else. The ocean floor is, in this light, not merely a scientific frontier. It is an ethical one. The decisions being made now about mining, about trawling, about the pace and priority of research funding, about the regulatory frameworks that govern human activity in the deep sea will determine what the ocean floor looks like for centuries. The organisms that live there, the processes that sustain them, the archive of planetary history preserved in the sediment, these are not renewable resources. They cannot be recreated once destroyed. The decisions made in the next decade or two will be permanent in ways that few other decisions are. This is a responsibility that falls on the societies with the technical capacity to both exploit and explore the deep ocean, primarily the wealthy, industrialized nations that have the ships, the instruments, and the economic interests most directly connected to what the ocean floor contains. The choice they make to exploit before understanding, or to understand before exploiting, or to refuse some exploitations entirely in recognition of what cannot be replaced, is a choice that will define what kind of planet this is for a very long time. The deep ocean does not vote. It does not lobby. It does not speak. It simply continues in the cold and the dark, as it has for hundreds of millions of years. The organisms that live there have survived mass extinctions, continental rearrangements, dramatic changes in ocean chemistry and temperature. They have not encountered, in all that history, a threat quite like the one that now approaches. The combination of rapidly changing chemical and thermal conditions, direct physical disturbance of the seafloor, and the removal of organisms by trawling and mining, all occurring simultaneously and at rates that give the slow metabolizing, long-lived communities of the deep ocean little time to respond. Whether those communities survive intact, whether the ocean floor that exists a century from now resembles the ocean floor that exists today, depends on choices that have not yet been made. The science that would inform those choices has not yet been done. The knowledge that would make it possible to say what is there and what is worth protecting, and what the consequences of various courses of action would be, this knowledge is, to a significant extent, absent. Feeling that absence is not merely a scientific goal. It is a precondition for making decisions that are not reckless for choosing what to do with the ocean floor on the basis of what is actually there, rather than on the basis of ignorance dressed as understanding. The ocean floor is too important and too fragile and too full of things that matter in ways we do not yet fully understand, to be managed on the basis of what we happen to know from the small fraction of it we have examined. The ocean is waiting. It has always been waiting. What it is waiting for now is not just curiosity and science, though both are needed, but the will to take it seriously, to resource the exploration it deserves, and to protect what exists before the opportunity to know it has passed. The deep is patient. The question is whether we are. Rest now. The ocean floor is patient. It has been here for longer than we can comprehend, and it will be here long after we are gone. But the questions it holds about life, about climate, about the history of the earth, about where we came from and what we might find beyond this world are ours to ask and ours to pursue. They are waiting in the dark and the cold and the silence, as they have always been. The ocean is always waiting. If this journey moves something in you, if the mystery and the importance of the ocean floor stayed with you through the night, consider subscribing to Sleep on Deep. Every week, we descend a little further. The ocean is waiting.